Alright, starting a little late, sorry, forgot. Second equation, second problem on that sheet that's linked in Canvas. So, we don't know, this is what, we start apart, they end together. Sum of all my momentum, 2 momentums before, 1 momentum after, this is what momentum expanded out is. My bucket starts with no velocity, therefore my bucket has no momentum. Now, when I go and I start plugging in values where I can and keep a variable where I don't, I find that I have MA times 10 plus 0, not necessary, but I'll put it there just for the time being, is equal to MA plus 0.25. That is the mass of AB. That's the expression that we can use for for object AB, and then we're going to multiply by the velocity, which is 7. The thing algebraically we just got to remember to do is we have to distribute this 7 to both things in the equation. So we end up with 10 MA is equal to 7 MA plus 1.75. Combine like terms and solve, and then at this point we subtract 7 to the other side, which is 3 MA is equal to 1.75. Then we divide both sides by 3, and we get a final mass of object A to be 0.583. I skipped some of the algebra from there. We distribute, combine like terms, so. We okay with that? We're just solving for a different variable. All right, then let's flip that paper over. The last calculation that I'm going to show you for this unit is one that differentiates between elastic and partially inelastic. So elastic and partially inelastic, they could have no distortion. They both start apart, end apart. They both have momentum being conserved. The difference is kinetic energy is conserved in the elastic, where it's not conserved in a partially inelastic. So this particular problem, this is the one that we started with on the front. It starts apart, end apart. I don't know if this is partially inelastic or elastic, based upon doing this calculation. We could, I'm not going to, but we could go from here to calculate what it is. But the idea is we can go through and I can, when I'm trying to determine whether it's kinetic energy is conserved, the way I've kind of found throughout the years is to have students go through and sum up your kinetic energy at location 1, which means I add all the kinetic energies of all the objects at location 1. So in this particular problem, this is from the front, I know. I take the kinetic energy of this plus the kinetic energy of this, and I get some number. Then I go through and I sum up all my kinetic energy at location 2. So I have 2 objects, the kinetic energy of this plus the kinetic energy of this. Notice I'm saying kinetic energy, not momentum. And then I get a number. And then I compare. And the idea of this is if the sum of all my kinetic energy before equals the sum of all my kinetic energy after, then KE is conserved. Okay? So if I go through and I sum up this number, I get something, and I sum up this number and I get something. If they are the same values, then kinetic energy is conserved. And if kinetic energy is conserved, then I look, oh look, kinetic energy is conserved, that's an elastic collision. If the opposite is true, right, if these do not equal each other, then it is not conserved, which then would mean it's a partially inelastic. That's the idea. So if we take a look at the problem on the back, it's similar to the problem I'm erasing right now from the standpoint that the objects start apart and they end apart. So we have object A is moving towards object B. They start apart. After the collision, they end apart. Object A and B are moving separately. So there are two objects that slide along a frictionless string. Ball A, let me erase my arrows. I got lazy. Didn't redraw my amazing pictures because they take a really long time to draw. Ball A, which has a mass of 0.4 kilograms, is moving to the right at 0. How do I know it's right? Because I'm choosing it to be the right. At 0.035 meters per second. Oh, it says to the right, never mind. When it collides with ball B, mass of B, which is 0.6 kilograms, that was initially at rest. If after the collision, ball A is moving to the right, nope, to the left, sorry. If after the collision, ball A is moving to the left, velocity of A after the collision, left, negative 0.007 meters per second, how fast, BB2, question mark, will object ball B be moving? Okay, so there's my quick picture. These objects are 0.4 kilograms because they didn't lose any mass, and this is 0.6 kilograms because they didn't lose any mass. I'm going to kind of go relatively fast through the conservation of momentum calculation, so if there's something you kind of get like, what? Just speak up. But it's a sum of all my momentum before is equal to the sum of all my momentum after. We start with two objects, so I need to have two momentums before I end up with two objects, so I need to have two momentums after. In order to calculate momentum, we take mass times velocity, mass times velocity, mass times velocity, plus mass times velocity. The VB1 is 0, so the object B doesn't have any momentum to start with. 0.4 times 0.035 is equal to 0.4 times negative 0.007 plus 0.6 times VB2. Okay, so if I multiply my line in purple, the numbers that I plugged into my equation that I had in green, I get numbers in blue, which then I just skipped a couple of algebraic steps, combined like terms, shifted VB, well, added 0.0028 to the other side to give, and then divide by 0.6 to get 0.028. These numbers are small, and these decimals are pretty important. In order to get these numbers to work out, we have to have a fair amount of decimals, so try to keep as many as possible, minimize the rounding at all possible. So that's the type of calculation we've done thus far. That's not new. The new part of this is conservation of momentum, is when we try to figure out if kinetic energy is conserved, I have to go through and determine, well, how much kinetic energy did it start with? And then I'm going to calculate how much kinetic energy does it end up with, and then if they equal one another, then I can say kinetic energy is conserved, which then would tell me it's an elastic collision. If they don't equal each other, then I'd say it's not conserved, which then would tell me it's a partially inelastic collision. So I'm going to sum up my kinetic energy at location 1. I'm going to sum up the kinetic energy at location 1, not of A, not of B, at location 1. So in order to sum up the kinetic energy at location 1, I add all the kinetic energies of all the objects prior to the collision. So I have two objects before, so I need the kinetic energy of object A at location 1, and I'm going to add it to the kinetic energy of object B at location 1. Kinetic energy of A before plus B before. What is this kinetic energy plus this kinetic energy? Not momentum, kinetic energy. Kinetic energy is 1/2 ma VA1 squared, 1/2 mv squared, plus 1/2 mv vb2 squared, 1/2 mv squared. Remember that my VB, erasing, that's VB1, VB1. Okay, that should have been 1, I wrote a 2 by mistake. We said VB1 was 0, so that whole kinetic energy of object B at location 1 is 0. So kinetic energy, the sum of all my kinetic energy at location 1 is 1/2 times the mass, 0.4, times the velocity that it started at, which is 0.035. Please do not forget to square your kinetic energy, or I'm sorry, your velocities when determining your kinetic energies. And we get kinetic energy, the sum of all my kinetic energy at location 1. Let me double check that number quick. Nope, 4.5. Oh, and not enough zeros. Okay, so it's 0.0000245 joules. This is the sum of our kinetic energy at location number 1. Then I repeat the calculation, but this time I do it at location